I will be presenting Agreement Implies Accuracy for Substitutable Signals, which is joint work with Frongillo and Waggoner. I will start with some background in order to motivate our problem. There is a small but fascinating literature in computer science on the problem of agreement. Suppose that Alice and Bob each have private information that leads them to disagree about the value of some quantity y. They want to exchange part of their information in order to reach agreement about y. Now, of course, they could exchange all of the information that they have, and then they will agree, but that is potentially very costly. And so the question for theoretical computer scientists is, how can they reach agreement efficiently from the standpoint of communication, if that's possible at all? The answer turns out to be that yes, it is possible. But even if they reach agreement, they aren't necessarily correct. And so our work aims to bridge that gap. Formally, we will say that there is a probability distribution over states of the world, as well as a random variable y, which is what Alice and Bob are trying to estimate. Alice learns a signal sigma, which is her private information about y, and Bob learns a signal tau. Now, together, all of these things constitute an information structure, which fully describes the setting. As an example, you could imagine that y is a random integer between 1 and 20. Alice learns whether y is greater than 10, and Bob learns whether y is prime. We can represent the situation in this 2x2 table of signal pairs. Now, even before Alice and Bob communicate, they each have an estimate of y. Alice's estimate is the expectation of y conditioned on her signal sigma. And similarly, Bob's estimate is the expectation of y conditioned on tau. Then Alice and Bob communicate according to some protocol, after which Alice has a new estimate of y, which is the expected value of y conditioned on both sigma and the protocol transcript. And similarly, Bob has a new estimate of y. And the goal is for Alice and Bob to agree. More formally, we will define capital T to be the set of signals that Alice believes Bob could have after communicating. And similarly, S to be the set of signals that Bob thinks Alice could have. Then we will define mu sub sigma T to be the expected value of y conditioned on Alice's signal sigma and on Bob's signal belonging to T. This is Alice's guess about y at the end of the protocol. And similarly, we define mu s tau to be Bob's guess about y at the end of the protocol. And our goal is for these two numbers to be similar. As an example, suppose that Alice and Bob each have 10 possible signals, and that in fact, Alice's signal is sigma 5 and Bob's signal is tau 8. As illustrated by this yellow cell. Now, Alice begins by communicating some partial information about sigma. So let's say that Alice says that sigma is one of sigma 3 through sigma 7. Then Bob communicates partial information about tau. So maybe he says that tau is one of tau 7 through tau 10. Then Alice responds saying that sigma is one of sigma 4 through sigma 6, and at this point we will say that the protocol ends. And at this point, Alice and Bob both know that the true state of the world lies somewhere within this rectangle. Furthermore, Alice knows sigma, and so she knows that the world state is contained in one of these 4 red cells. Whereas Bob knows that we are somewhere inside one of these 3 blue cells. And so Alice's estimate of y is the average value of y over all world states contained in the red cells, whereas Bob's estimate of y is the average over the blue cells. So if all of these cells are equally likely, and the average value of y inside each cell is as indicated here, then Alice's estimate of y will be the average of 0, 2, 4, and 6, which is 3. and Bob's estimate will be the average of 2, 3, and 4, which is also 3. And so in this particular situation, Alice and Bob will agree. Now, it turns out that exact agreement isn't always computationally tractable. But what about approximate agreement? So formally, we will say that a communication protocol causes Alice and Bob to epsilon agree if, after running the protocol, the expected squared distance between Alice's estimate and Bob's estimate is at most 4 epsilon. Never mind the 4, it is there for reasons of technical convenience. But the intuition is that this means that Alice and Bob are close, on average, over nature's random choice of the state of the world. In 2005, Scott Aaronson exhibited a protocol that allowed Alice and Bob to efficiently reach epsilon agreement. The protocol was quite simple and natural. First, Alice sends Bob her expectation of y. Then Bob responds with his expectation of y conditioned on what Alice sent him. Then Alice responds with her updated expectation of y, and so on. Now, if you're worried about the fact that communicating a real number takes potentially arbitrarily many bits, note that this protocol can easily be coarsened so as to avoid this issue. With this background in hand, I can now motivate and state our problem. If Alice and Bob follow Aaronson's protocol, they will end up with roughly the same estimate of y. But is this estimate necessarily accurate? Unfortunately, the answer is no. Consider this information structure, called the XOR information structure. Here, Alice and Bob each receive independent random bits as their signal, and the value of y is the XOR of the 2 bits. No matter what, Alice and Bob's estimate is 0.5 at the start, and so they agree immediately. But the right answer isn't 0.5, it's either 0 or 1. By the way, when I say the right answer, I mean the expected value of y conditioned on both Alice and Bob's signals. That's what we will be benchmarking Alice and Bob against. Formally, we will say that Alice's estimate of y is epsilon accurate if Alice's expected squared distance to this benchmark is at most epsilon. Now, agreement does not in general imply accuracy, as we just saw. And so it's natural to ask, under what conditions does agreement imply accuracy? That is, we want to fill in the blank in the following theorem statement. Suppose we have an information structure, and suppose that after communicating, Alice and Bob epsilon agree. Under what conditions on this information structure can we then say that Alice and Bob are fairly accurate? I will now tell you how we filled in the blank. But first, it is useful to understand what went wrong with the XOR information structure. Here's my diagnosis. In the XOR information structure, only knowing one of the 2 signals was completely useless. You really needed to know both. And so while Alice and Bob agreed from the start, their agreement was superficial. It was based on ignorance. This is closely related to a notion called informational substitutes and complements, which intuitively speaking means how useful it is for only one signal, how useful it is to know only one signal in order to get an estimate of y. As an example, the XOR information structure is an example of informational complements, because knowing only one of the 2 signals is totally useless. On the other hand, if Alice and Bob receive the same signal, then knowing that one of those 2 signals, it tells you everything you need to know. So that's an example of informational substitutes. So it's natural to wonder whether some notion of informational substitutes can be used to fill in the blank. And the first natural notion to try is weak substitutes, which was introduced by Yiling Chen and Bo Waggoner. Weak substitutes is about how much your estimate of y improves from learning sigma. In particular, weak substitutes says that the expected amount that your estimate improves from learning sigma is larger if you're starting from a state of ignorance than if you already know tau. So for example, suppose that sigma and tau each both tell you the value of y. Then learning sigma improves your estimate of y if you don't know anything. But if you already know tau, then it doesn't. So this is an example of weak substitutes. On the other hand, the XOR information structure does not satisfy weak substitutes. That's because if you don't know anything, learning sigma does not improve your estimate. Whereas if you already know tau, then learning sigma tells you everything you need to know. Now, it turns out that the weak substitutes condition is insufficient in order to guarantee that agreement implies accuracy. Now, recall that a communication protocol subdivides the space of signal pairs into rectangles. And so what we will require is that weak substitutes be true, not just on the entire information structure, but also on every subrectangle. We call this condition rectangle substitutes. And that is what we used to fill in the blank. So here is our main theorem statement. Suppose that we have an information structure that satisfies rectangle substitutes. And suppose that a communication protocol causes Alice and Bob to epsilon agree. Then Alice and Bob are also fairly accurate. In particular, they are 10 epsilon to the 1/3 accurate. I won't give the full proof, but I will sketch the main idea. Here is our space of signal pairs as before, and suppose that the particular pair of signals is as given by this yellow cell. Alice starts by communicating some partial information about sigma. Bob responds with partial information about tau. Alice responds with partial information about sigma, and let's say that the protocol ends there. And let's zoom into this rectangle. Now, we know that Alice and Bob approximately agree. That is our given. And what we want to show is that Bob's estimate is fairly accurate. In other words, that learning sigma won't give Bob much information about y. So let's say concretely that Bob's estimate of y is 3.53. Because Alice and Bob approximately agree, Bob knows that Alice's estimate is likely to be somewhere between 3.5 and 3.56. So let's focus in on the rows corresponding to Alice's signals that have this property. These rows are outlined by this red rectangle, and we will use weak substitutes on this rectangle. Now, on this subrectangle, learning sigma gives almost no information about y. That's because no matter which row we are in, the expected value of y conditioned on being in that row is within some narrow range, 3.5 to 3.56. Now, by weak substitutes on this rectangle, it is also true that if you know tau, just like Bob knows tau, then learning sigma still gives almost no information about y. And so to conclude, what this means is that Bob knows that we are probably in this red rectangle. And furthermore, if we are in this red rectangle, learning sigma will give Bob almost no information about y, which is what we wanted to show. I will now briefly mention some extensions of our work. The first one is graceful decay. Rectangle substitutes is a pretty strong notion, so it is natural to ask whether agreement implies accuracy for information structures that are close to rectangle substitutes. And the answer turns out to be yes. Our second extension goes beyond squared distance to other notions of Bregman divergence. While all of our notions that we've discussed, from agreement to accuracy to substitutes, have been based on squared distance as the measure of error, In some situations, other notions of error are more appropriate, such as Kale divergence or other notions of Bregman divergence. And so in this paper, we give a protocol for epsilon agreement with respect to an arbitrary Bregman divergence. We then show that if an information structure satisfies rectangle substitutes with respect to a Bregman divergence, and that Alice and Bob approximately agree with respect to that divergence, then they are also approximately accurate with respect to that divergence. There are several exciting directions for future work. Probably the one that I'm most excited about is incorporating strategic constraints. That is, so far we've been modeling Alice and Bob as truth-seeking agents who are willing to follow any protocol. But now we could instead model Alice and Bob as strategic agents, and that they communicate via buying and selling shares in a prediction market.